So we continue the chapter sound, and we are on the condition for hearing an echo. We just understood the definition of an echo, that echo was the reflected sound heard after the original sound ceased. Okay, so that is an echo. Now the condition required for an echo is, firstly, let's understand this thing in a biological way also. Now we can hear a distinct sound. Okay, our brain can understand a distinct sound in a time difference of t is equals to 0.1 second. If I'm able to hear something at a distance of 0.1 second, I can hear it as a proper sound. Okay, if I am hearing something, and if I'm hearing two sounds, okay, I'm hearing two sounds, and these two sounds are produced or are coming to my ear in a span of within 0.1 second, then I hear both the sounds simultaneously. Okay, अगर वो 0.1 सेकेंड के अंदर ही दोनों मेरे कान के पास आते हैं, तो I can understand them as together. They'll be like superimposed over each other, so they will be combined to each other. But if I am getting sounds after 0.1 second, then my brain can understand it as a separate sound. So that means the persistence of hearing, okay, we can hear a certain particular kind of a sound clearly and distinctly if it comes to us after 0.1 second. So that's what we are saying over here, that an echo is heard only if the distance of the person producing sound from the rigid obstacle or reflector is long enough to allow the reflected sound to reach the person at least 0.1 second after the original sound is heard. So only if the original sound is going to be heard, and after that, after 0.1 second of that, we are able to hear another sound, only then that particular sound will come to us as an echo. The reason is the sensation of the sound persists in our ears for about 0.1 second after the exciting stimulus ceased to act. So since there was a stimulus, okay, मैंने एक particular sound सुना, okay, I heard the sound, and that sound was hit my ear, and it generated the auditory kind of a impulse to my brain to understand that sound. So वो जो है, it is going to take 0.1 second. So once it is after 0.1 second, I understand it as a separate sound. So that's why hence to hear the echo distinctly separate from the original sound, it must reach the ear at least 0.1 second after the original sound. So only if the echo is able to be coming back after 0.1 second from the original sound, then only I can hear it as a separate sound. If I am hearing it within the same 0.1 second, it is not going to be a separate thing. It will be a continuity of that old one, or maybe it is not heard even by the continuity, it will be just together. Both of them will be together. Like in this, let's take this room. Okay, in this room, when I'm speaking, do you hear an echo? No, you don't hear an echo. Why do you not hear an echo? Because whatever reflection of the sound is taking place, that particular sound is hitting your ears at the same time. Okay, it is hitting the ears at the same time when the original sound is coming. So because the distance is not that big, that it would go and come back, and that's the reason what will happen is that the original sound and the echo, if at all it's there, is going to reach your ears at the same time, and hence you do not understand it as a separate sound, and hence it is not an echo. So for an echo to take place, the most important thing is that it will require to come or reach our ears 0.1 second after the original sound has been ceased to exist. So that is the first thing. So let's understand that what is the minimum distance required for an echo to be formed by any particular reflecting medium. Like for example, if I want to make a complete big hall wherein I want that echo should take place properly, then I should know that when I'm speaking over here, if the speaker is at one end, at what distance should there be an obstacle or the wall, so that that I can hear that particular echo very prominently. So for that thing we can have a small calculation done. So what we do is that if the distance of the get D is the distance of the observer from the obstacle and V is the speed of the sound in the medium. So we know that if suppose this is the observer or the person who is going to make the sound, so he is going to produce the sound over here, and this is the obstacle over here, and the distance between this and this over here is, let's say, D. The velocity with which the wave is going to travel is going to be V over here, and you know that for the wave to go and come back, it will be automatically D plus D or 2D. So we have over here that if D is the distance of the observer from the obstacle and V is the velocity of the sound in the medium, then the total distance traveled by the sound to reach the obstacle and then come back is 2D. So because the sound which is going to be heard will be an echo, if this sound goes here, hits this thing and returns back over here. So it has traveled D distance earlier and D distance coming back. So the distance traveled will be equal to 2D. The velocity will be V. Okay, and we know that the time taken should be equal to 0.1 second. The minimum time taken for it to be is 0.1 second. Accordingly, we can have this particular kind of equation here, that what will be the distance D in this case. So we can see the time taken for the echo or the reflected is T is equals to 2D upon V. So D is equals to V into T upon 2, or because it is nothing but okay, so one second. Okay, what we have is distance is equals to, we know distance is equals to, about velocity is equal to distance upon time. Velocity is equals to distance upon time. So distance into time is or velocity upon time is equals to the distance traveled. Now, so accordingly we can say you have over 2D is equals to this much. So D is equals to V upon 2T. Okay, and so the distance, what will be, now we know that the velocity of sound in air is equal to 340 meter per second. So that will give me D is equals to, D will be equal to 340 upon 2 into 0.1, because the time taken is 0.1 second. So this will be 170 and this will be equal to 170016. Sorry. What happened? Let me go through them again. We know the velocity is equal to distance upon time. So distance is equal to velocity into time. So distance travel, so D is equal to 2D, because the distance travel is from here and back over here. So 2D, so therefore 2D is equal to V into T. And we have over here D is equal to V into T upon 2. The V is 340 and time is 0.1 upon 2. So that will be 34 upon 2 is equal to 17 meters. So the distance, so the minimum distance required for an echo to be heard distinctly should be 17 meters. So it should be only if an obstacle is 17 meters from you, only then you can expect that there could be an echo formed by the sound what you are being producing. So we can see that thus putting T is equals to 0.1 second and V is equals to 340 meter per second in air at ordinary temperature, for equation we get D is equals to 17 meters. Thus, to hear an echo distinctly, the reflecting surface in air should be at a minimum distance of 17 meters from the listener. If the distance is less than 17 meters, the reflected sound which will reach the ears before the original sound dies out, and so no echo will be heard. So That's what we are understanding, that if the distance traveled is not 17 meters, but if it is less than 17 meters, then what will happen is the time taken for the sound to echo and come back to us will be less than 0.1 second, and that's the reason it will just get merged with the original sound, and hence we will not hear it as an distinct echo. So that's why we see that if the reflector is at a distance less than 17 meters, the reflected sound gets mixed with the original sound. Also, if there are repeated reflections at the reflecting surface, the sound gets prolonged. This effect is called as reverberation. Like for example, if you go to Taj Mahal or any cave, you will find that अभी हम लोग बोलते हैं हो तो हो ऐसा करके पूरा वो होता है, and that is like a continuous form, not a distinct kind sound, but it is going to be echoed again and again, again and again. So वैसे जब भी हुआ, and it is getting prolonged. Okay, when the whole sound gets prolonged. So that is called as reverberation. So this effect is known as reverberation. It can be easily be experienced in high tombs like Taj Mahal, Sikandar, etc. So thus the echo, to hear the echo distinctly, the following three conditions must be satisfied. So now we come to the main things. What are the three conditions required for a distinct echo to be heard? First thing, the minimum distance between the source of sound and the reflector in the air must be 17 meters. It is different in different medium depending upon the speed of the sound in the medium. For example, inside seawater, it will V is equals to 1400 meter per second. So D will be equal to 70 meters to hear echo distinctly. The obstacle in the seawater must be at a minimum distance of 70 meters from the listener. Second is the size of the reflector must be large enough to as compared to the wavelength of the sound of the wave that we already discussed earlier, that the obstacle should be large enough as compared to the wavelength of the sound. And the intensity of sound should be such that the reflected sound reaching the ear is sufficiently intense to be audible. Now this is also very important. So this is like the sound, like if I go even to the best of the echo point and I just say, Bhavin, will it be echo? No, I will need to really scream out over there. Why is it required? Because the intensity of the sound should be such that it should be able to travel the distance, hit that area and return back, and when it returns back, it should be able to be of that much amount of intensity that it is audible to me. Okay, so that's why it is very much required that the sound intensity should be loud enough that it can go and return back with that much amount of intensity that it could be still audible. It should not be so faint that it is not audible to us. That's why you need to really scream in a echo point. Okay, so the 3 points, or the 3 kind of factors which an echo will be called will be: first is minimum distance in air is equal to 17 meters. Of course, depending upon the medium, like for example, they given you that if it is seawater, then the seawater, the speed is not 340 meter per second, but it is 1400 meter per second. Hence, the minimum distance required for the obstacle to be there will be 70 meters. So that is first point. The second point is the size of the obstacle. The size of reflector should be good enough or bigger than the wavelength of the size of the reflector, greater than lambda, that is wavelength of the wave. And thirdly will be that the intensity should be high enough that it can be should be greater enough so that it can travel and reach back to us. So that is why these are the 3 conditions required for the distinct echo to be heard. Now the echo has got many applications, because of the fundamental principle of echo taking place. This is used in a large scale in different kinds of forms. So we can also say that by listening to the echo, we can also find out that what is the speed with which the sound is traveling in air. So determination of speed of sound by the method of echo. The echo method can be used to determine the speed of the sound in air. For this, sound is produced from a place at a known distance, say distance at 50 meters away from the reflecting surface. The time interval t in which the echo reaches the place from where the sound was produced is noted by the stopwatch, having the least count as 0.01 second. Then the speed of the sound is calculated by using the formula v is equals to 2d upon t. So the experiment is repeated several times, and an average value of speed of sound v is determined. So it's something like this only, that you are standing here, you place an obstacle at a distance of 17 meters or so, and then you are starting a stopwatch. As soon as you scream out or you give a loud sound and you start the stopwatch, and hear the sound again and you stop the stopwatch, to know that what is the time taken for that particular distance to be traveled 2 times. So in the formula, what we'll be using will be v is equals to 2d upon t. Why 2d? Because one way d and second by return is d. So that's why distance traveled by the sound is not just d, but it is 2d. That's why for an echo, the speed of the sound to be found out with the help of an echo, it will be 2d upon t. Other uses of echo are: echoes find their applications in sound ranging and echo depth sounding by using the ultrasonic waves. The ultrasonic wave frequency about 20 kilohertz are more energetic than the audible sound. So they have the following 3 properties for their wide use. So it is seen that the sound waves are also used to determine the distance between two surfaces. Like for example, inside the sea, if you want to find out that how far is the iceberg, or how far is the depth of the sea, or how far is the shoal of fishes over there, we take this particular method of using ultrasound for its determination. And you are using ultrasound because of its 3 very important properties of ultrasound. So ultrasonic sounds are the one which are about 20 kilohertz. So because of the very high frequency, they are highly energetic waves. You can understand kitna high kinetic energy uske andar hai, that in 1 second it is moving 20,000 times. So that's why it is a sound which is extremely energetic, or the waves which are extremely energetic waves. So we find that the 3 properties which are going to make it so ultrasonic के properties में first property of ultrasonic, they travel undeviated through long distances. So that means they are going to travel undeviated. So they are undeviated. Why they are undeviated? Because of the high penetration power. Why they are having penetration power? Because of the high momentum. What is the momentum over here? Momentum is nothing but the velocity with which they are traveling. The velocity, the frequency with they are traveling, because they are highly energetic waveforms. So the energy is with which they are moving is very high. So that energy which is there in it is allowing it to have a good amount of penetration power. Second is they can be confined to a narrow beam. So they can be confined to a narrow beam because they can go straight line. So they can be confined to a narrow beam. So narrow beam form mein it can be sent. It will not get spread or scattered so easily. So that's the thing, that they are going to be undeviated and they're going to travel a narrow beam, and they do not easily absorb in a medium. So low absorption, so not absorbed. Normally what would happen with the sound if they can get absorbed in the medium, and that's the reason many of the places, like for example when we are talking about the थिएटर्स, नाउ थिएटर्स में तो डिस्टेंस जो है वो 17 मीटर से ज़्यादा ही है, फिर भी थिएटर हॉल में वी डू नॉट सी टू मच ऑफ एन एको. व्हाई इज इट सो? इज बिकॉज you are providing the walls of the theaters with the felt or velvet kind of a cloth all around, and the curtains around, and thick the carpets over there. So why is that so? Because these are the material which will absorb the sound waves. So the sound waves are going to be absorbed by them. That is called as acoustics. So in a theater hall, they will be trying to see to it that the echo will be formed the least. Whereas here what we require is that the ultrasonic are such that they are not getting absorbed so easily, and that's why they are able to be echoed easily and they could reflect back easily. So note, the audible sound waves frequency 20 Hz to 20,000 Hz do not possess the above property. However, the ultrasonic sound in the medium have the same speed as the speed of the audible sound in that medium. So These three properties are there only in the ultrasound and it is not there in the audible sound. But the only thing which is the same between the ultrasound and the audible sound is the speed of travel. So the similarity between ultrasound and audible sound similarity is that speed is same. So speed of the travel, or the speed at which they are going to travel, is going to be remain the same in that medium. So let's see what are the different uses of the ultrasound, or uses of the ultrasound also, of the echo in the different forms. So use of echo by bats, dolphins and fishermen. Animals have different audible range of frequency. For example, bats, dolphins and dogs have much higher upper audible limit than the human beings. Bats can produce and detect the sound of very high frequency up to about 100 kilohertz. Bats fly with a speed much lower than the speed of sound. The sounds produced by the flying bats get reflected back from an obstacle in the front of it. By hearing the echo, bats come to know, even in the dark, the location of the obstacle, so they can fly safely without colliding with it. This process of detecting obstacle is called sound ranging. So it is a natural way that the bats are going to use sound ranging, which normally we use in ships or in submarines or even in aircrafts. So the bats, they have a capacity to produce an ultrasound of the frequency 100 kilohertz. And this one, of course, the speed at which it is going to fly will be much less than the speed of sound. So when they are flying, they are going to give out that ultrasound waves, and that will hit the obstacle in front of it and return back. The bat automatically knows that how far is that particular obstacle from him, and accordingly he can divert his way, and hence the bats can even fly in the night time without getting hit by an obstacle. So that's why they are safely flying in the night time even without colliding, and this is called as sound ranging. Dolphins detect their enemy in obstacles by emitting this ultrasound waves and hearing their echo. They use ultrasonic waves for hunting their prey. So even the dolphins, they use the same method for finding out their enemies, as well as they are finding out their prey. For both these purposes, for finding out the enemies and to find out the prey, they are going. Dolphins also give out the ultrasound, and which is reflected back, and they come to know that where exactly is the next obstacle for them. A trawlerman or a fisherman send an ultrasonic pulse from a source or high frequency vibration vibrator into the sea and receive the pulse reflected from the shoal or fish in a detector. The total time t of the to and fro journey of the pulse is recorded. The distance d of the fish is then calculated by using the relation d is equals to vt upon 2, where v is at nearly 1400 meter per second, the speed of ultrasonic wave in seawater. So even the fishermen, they are also using this technique for finding out that where is the shoal of the fishes, so that they can spread the net accordingly. For this, the same thing they do is they are going to give a vibrator, that is the ultrasonic sound producer, into the seawater, and they give out the ultrasound in different directions, and they try to find out that where they are able to get a particular reflection of the sound, and they know that the speed of the ultrasound in the seawater is 1400 meter per second. So accordingly, the time taken for the sound to return back, that is calculated, and according to the distance at which the shoal is present, shoal of fishes is present, it can be identified, and they can spread the net accordingly in that particular direction. The use of echo by sonar. So sonar is sound navigation and ranging. So that is, the word sonar stands for sound navigation and ranging. Shows the principle of sonar in which ultrasonic waves are present in the seawater in all directions from the ship. These waves are received after reflection from an obstacle such as an enemy submarine, iceberg, sunken ship, etc. To find the distance of the obstacle from the ship, the time interval t between the instant of when the waves are sent and the instant when the waves are received after reflection from the obstacle is measured. So against the sonar, so the next thing what we see is sonar. Sonar is sound navigation and ranging. So it is sound navigation and ranging. So this sound navigation and ranging is done by, normally the ships use this thing, wherein the ship is going to give out ultrasonic sounds on in all the directions around it, and it is going to calculate that what is the time taken for the nearest obstacle to be there in front of them. So the nearest obstacle will be denoted when they can know that whether there is a sunken ship inside, or there is a iceberg around, or is a submarine around. So they can identify any kind of obstacle which is present around the ship in their course, and accordingly they can avoid a possible accident in future. Like the same thing, if sound navigation ranging would have been there, there would have been quite a huge possibility that Titanic would have not sunken. So this is an important thing, that the sonar is used to find out or detect the obstacle which is in the pathway for the ship. And for this, what they do is a simple thing, that they know that they from the time the sound has been sent across to the time the sound is received back, the time is noted, and then they are going to know that the speed at which the sound is going to travel in the water is 1400 meters per second. Accordingly, they will find out the distance which is going to be between the obstacle and the ship. So the distance d of the obstacle from the source is then d is equals to vt upon t. The v is the speed of the ultrasound in water. The depth of the sea can also be found by this method. The process is known as echo depth sounding. So when you are trying to find out the depth of the sea by using this particular method, we can say that it is the use of echo depth sounding. So echo depth sounding is the process by which you are trying to find out the depth of the sea below the ship. Note, in radar, radio detection and ranging, the echo method is used to detect the presence of an obstacle and also to find its range. A signal of electromagnetic waves such as the radio wave or microwave is sent in space, which after reflection from the object such as enemy aeroplane in its path returns to the radar itself. Both sonar and radar, the transmitters and the receivers are placed close to each other. In figure 7.1, they are shown separately just for clarity. So we can see in sonar and in radar. Radar is the radio detection and ranging. Now, radio detection and ranging uses the electromagnetic waves, that is the light waves kind of a thing, radio waves in fact. So they are going to use radio waves and microwaves for this purpose, which are going to be the one which can travel even without a medium, because they are light electromagnetic waves. And they are also going to use the same method, but the speed of course of light is absolutely very high. That's why it is faster to detect, and hence we can detect the sound ranging ke se zyada radar ranging will be much efficient and faster. But both in case of sonar and radar, the transmitter and the receiver both are placed at the same point. The transmitting and receiving is both at the same point. Only in the figure they are given transmitter here and receiver here. That is only for detection. That is only for the clarification in a particular figure. Otherwise, it's going to be the same point. Third is the use of echo in the medical field. Now you must have heard the sonography. Okay, you must have heard of sonography taking place for the kidney and the gallbladder for the kidney stone, or even for the pregnant mother for the baby to check the condition of the baby. So the sonography is also a kind of a sound wave, that is again ultrasonic. So sonography is nothing but ultrasonography. Actually, it is ultrasonography. So in medical field, echo method of ultrasonic waves is used for imaging the human organs such as liver, gallbladder, uterus, womb, etc. This is called ultrasonography. Similarly, echocardiography is used to obtain the image of human heart. So when we are doing the same thing for the heart, it is ECG. You must have heard the word of ECG. ECG is nothing, echocardiograph. Okay, so echocardiograph is also the graphy is also the method which is using the sound waves for imaging the organs of our body. So ultrasonography and the echocardiography are the, again, ultrasonic waves which are used for imaging the organs of our body. So this is about the different applications of the echo or the sonar and the different forms of echo over here. So this is about the expansion of the chapter. Now we move on to the numericals which are here. So there are totally 11 numericals in my textbook. So I don't know if the new chapter textbook there are some more or less. I can just we can just do as per my textbook. And if you have got any kind of difference in your textbook, you can just let me know. And if you have got any doubt in that, you can let me know about it. Okay. So that is about the numerical. I'll better take it in the next video. Okay.